Okay, so now we're going to talk about the energy of cycloalkanes. And remember, we're talking about energy because when we can consider systems that are lower energy, they're going to be more stable, right? Lower energy is going to be more stable. And things that are more stable are going to be more prevalent in equilibria. So energies matter, right? They're going to help us evaluate which direction reactions are going to go. So let's look at cycloalkanes. Now recall that for an sp3 hybridized carbon, the ideal bond angle is 109.5, right? 109.5. So if you want to get 109.5, you absolutely cannot get 109.5 if you're dealing with cyclopropane, right? Because the interior angles of cyclopropane are 60 degrees. I mean, the interior angles of an equilateral triangle are 60 degrees. And no matter how I twist that, I cannot get that into 109.5. It's actually twisting is going to make the angles smaller, right? So the same thing goes for cyclobutane. Cyclobutane cannot get into 109.5. And so we have something called angle strain, right? So no matter what we do, we twist that, we cannot get this bond angle, this carbon. See, can you see a carbon, carbon, carbon? If you can see those three carbons, the bond angle you can see is 90 degrees. We cannot get that into 109.5, and so we have angle strain, okay? The interior angles of a pentagon, however, are 108, right? And so you can see that we are close, very close to 109.5 here. So we have very little angle strain in cyclopentane. Now cyclohexane, the interior angles of a hexagon are 120 degrees, right? So if this was held flat, there would be angle strain there also, right? If this ring were held flat, then this would also have some angle strain. But don't forget, these things don't have to be held flat. What I did to prepare for this conversation was I went to WebMo and let me go back again. File. Let me go back again. I went to WebMo and I made a couple molecules because I don't have a model set and we're not working together in the same room. So WebMo. Thank you, honey. Thank you. All right, so I'm gonna log in here. And I made some molecules. I made cyclohexane, chair, right? There's one. So new job, import job, file type, XYZ. Cancel. Create new job, file, import molecule. XYZ, browse, cyclohexane chair, open. Okay, now watch this. Clean up, generate bonds, okay? Now watch this. So this, you see that the carbons are not held in a plane. Can you see that they're offset? And these guys can get to exactly 109.5. Amazing, it's beautiful, isn't it? So here's a carbon, here's a carbon, here's a carbon, 1, 2, 3, 4, 5, 6. And those are all hydrogens that are up and down and pointing out. That is a cyclohexane molecule that is offset, and they can get into 109.5. That's beautiful. Now, the interior angles of a heptagon are 129, and so there would be ring strain there also if it was held flat, and so on. Okay? All right, so now it turns out that the most stable one, believe it or not, well, maybe you believe it because I just sort of pointed at it, is if there are 6 carbons. So what these, let me walk you through these data. So what happens is all of these are subjected to combustion analysis, okay? And here are the amounts of kilojoules per mole that you get out. That's what this is, okay? Cyclopropane, which has 3 carbons in it. Cyclobutane has 4. Cyclopentane has 5, right? You see that? Cyclohexane has 6. Now, this is now divided, but sort of normalized over how many CH groups you have in there. So cyclopropane This is divided by 3 because there's 3 CHs in it, right? And that goes to 697. Excuse me, cyclobutane is divided by 4 because it has 4 CH2s in it, and it goes to 680. Excuse me. Cyclopentane, 658. Look at that, 653, 657. And then those numbers are graphed here, and we see that the lowest energy, that is the most stable per CH2 group, is cyclohexane, right? And the reason is because, let me go back a slide. The reason is because we have, if we twist the carbons, right, then there's no angle strain. So if you look down on that, those are exactly 109. Well, you can't see that from there, but that's exactly 109.5, okay? And we also have no torsional strain, right? Remember the torsional strain we talked about in our last conversations? These hydrogens are not eclipsed with each other. And if we look along, that's looking along that dihedral. Let's look along this dihedral. You see that? These are staggered. Can you see that? These are staggered. All right. And this is sort of like a methyl group and a methyl group. So those are gauche with respect to each other, right? Did you write that term down with our last conversation? These are gauche. You've got a CH here and a CH here, and they're only 60 degrees away from each other if you look down that dihedral. But there's no torsional strain and no ring strain. Okay, there's just some. I'm sorry, there is a little torsional strain because we have. These guys are gauche with respect to each other, but where am I? All right, because there's a minimal amount of torsional strain. All right, so let's go back here. So this was the graph that showed you that if we see how much energy is in cyclopentane total, it'd be 2091 divided by 3, we get 697 because it has 3 carbons in it, right? And we see that cyclohexane is the most stable. All right, so look at cyclobutane. Cyclobutane is 27 kilojoules per mole less stable than cyclohexane per CH2 group, and that's because it's worse than this, right? If you take let me upload cyclobutane. File, import molecule. I made these in advance so we could quickly pull them up. But you could make these too. It's free. Clean up, generate bonds. And it's free and it's online. I showed you, I think, the other day how to figure that. So, okay, so there's cyclobutane, right? Can you see that? And can you see that those hydrogens are eclipsed? Look at that. Those hydrogens are eclipsed, and these methyl groups are eclipsed also. So we not only have ring strain because this angle is too tight, we also have torsional strain because these hydrogens are eclipsed. All right, and that's what this picture is here about. Now, it turns out, believe it or not, if this ring gets puckered, right, so instead of having 90-degree angles on the inside, if that's puckered, we lose some of the torsional strain. All right, so remarkably, cyclobutane's not flat, all right, which is amazing. All right, cyclopentane is only 5 kilojoules per mole less stable than cyclohexane per CH2 because there's very little angle strain. The bonds are 108. The bond angles are 108 when it's flat, which is very close to 109.5. And there's slight torsional strain because these are sort of held into place, but this cyclopentane adopts something called an envelope conformation, and that sort of helps alleviate that torsional strain between the eclipsed hydrogens.